Welcome, everybody, to CS 189, or if you're a graduate student, to CS 289A. My name is Jonathan Shuchak. I'll be taking you through this semester in the very fascinating world of machine learning. There is a web page for the class where I've written the URL up there. That is the place to start for finding all the resources that you will need this semester. For those of you who are not enrolled yet, or say concurrent enrollment students who haven't been admitted to the class yet, all of the resources you need to get started and follow along the class in hopes of getting into the class will be available even if you're not enrolled. So anybody can add themselves to the Ed Discussion group, which is linked from the class webpage. Anybody will be able to add themselves to Gradescope once we create the Gradescope instance for this class, which we haven't done yet. If you have questions to ask throughout the semester about almost anything, I would prefer that you ask most of the questions on Ed Discussion. If some of you aren't familiar with Ed Discussion but are familiar with Piazza, Ed Discussion is essentially the new message board that the university has mandated as a replacement for Piazza. Now, If you have a very personal question that you don't even want the TAs to know about, you can send me email. But I want to be clear that throughout this semester, while this class is in session, I will be checking ed discussion far more often than my email. My email is kind of a neglected swamp, and when I'm teaching a course, it's even more neglected. Whereas ed discussion is, something I check multiple times a day to keep the class going. Also, ed discussion has an option for private questions. So if there's a question you don't want the rest of the class to see, you can make it private and just me and the teaching assistants will see it. Having said that, if the answer to your question might be useful to someone else in the class, it's usually preferable to make it a public question so that everybody can benefit from the answer. But private questions are more appropriate in certain special cases, like something really personal you don't want to share, or if you want somebody to look at a big chunk of code, you should not be sharing large chunks of code online with your fellow students, please. There will be discussion sections, not this week, they start next week. They'll be on Tuesdays and Wednesdays. The discussion sections are essentially wide open. You can attend any section you want. You can attend as many sections as you want. You can attend a different section every week. We're flexible. We will probably have a TA doing as well an online recording of a walkthrough of the discussion section material each week. So if you can't get here in person, that'll probably be available, but no promises. We might miss a few weeks. We'll see what happens. Also, we might or might not, we're going to have to figure this out with the TAs in the coming week, have a few special discussion sections. Usually the two most common ones are, in the past few years, we've always had a section devoted to going through old exam problems. And sometimes we've had sort of an advanced section where a graduate student tells you about the cool new research in the field for a few minutes at the beginning of some of the sections. We'll see what happens this semester. But sections start next Tuesday, so please take advantage of them. They can help you a lot with understanding the material in this course. Homework 1 is available already from the class webpage, so check that out. You have 1 week to do it. Naturally, a lot of you are worried about enrollment. There's currently a maximum of 630 students here that we can admit. That is both 189 and 289A added together. Can't go over about 630 students, and we probably won't increase that, but I won't say 100% for sure yet. So right now there's about 312 students on the wait list, not counting prospective concurrent enrollment students. We are expecting many people to drop the class this semester. So in the past, typically historical numbers are 100 to 200. We'll see what happens this semester. So if you're in the first 150 on the wait list, your hopes are pretty good. We are prioritizing in the sense that EECS grads have the highest priority. So if you're an EECS grad, you should be getting into the course. And if you haven't yet, let me know. Undergrads second, and we're going to prioritize them according to the way the registrar prioritizes them. And non-EECS grads are third priority. I don't think that we will be admitting any more concurrent enrollment students than we already have, but that's not 100% certain yet. So sorry about that. If that changes, I'll certainly let you know within the week. This class has a couple of textbooks that are available free online, and let me show you what those look like. They are An Introduction to Statistical Learning by James Whitten Hastie and Tibshirani, and The Elements of Statistical Learning by Hastie, Tibshirani, and Friedman. Some of these people are very famous statisticians. The books are pretty good. They don't cover everything we'll need, but they cover a lot. They're great references. They're kind of written from a statistical point of view, a statistician's point of view, which means they're weak on computer science content, which is fine for what they are. We're going to be adding more computer science content this semester. You should, as you're going through this class, keep abreast of the recommended readings on the class webpage. Those are, well, I'm not going to be reminding you every lecture that there are readings that you go read them. I'll just be giving lectures, and it's your responsibility to keep up with the class webpage, which lists all the reading that I want you to do this semester, and try to keep up with it as a reinforcement for the lectures. Are there any questions so far? Wow, okay. Let me talk a little bit about what you need to survive this course. So I'm calling this prerequisites, but these prerequisites are not enforced by anything other than your own recognition that you are or are not prepared for this course. So I want to give you a sense of what you need to know, and if you don't have most of these nailed down, you might want to reconsider taking this course. If you're strong in most of them but weak in one, you might want to consider using the next week wisely to, the next 3 weeks really, wisely to reinforce your skills. So you'll need to know some vector calculus for this course. It helps a lot if you've taken Math 53, but in general, exposure to gradients, having an intuitive understanding of gradients, that's what we really need from you. So they're not all aspects of vector calculus. We don't care if you understand div or curl, but gradients are really important in this semester. A bigger chunk of things that you need to know is linear algebra. And if you've taken Math 54 or Math 110, or say the electrical engineering series of 16A and 16B, then you're probably mostly well enough prepared for this class, but we're going to be using linear algebra so deeply that the more you review, the better. I want to mention that there are links on the class webpage to help you review this. I'm particularly fond of, there's a YouTube channel that gives beautiful animations and really wonderful explanations, intuitive explanations of the geometry of various linear algebra concepts. That's linked from the class webpage, so if you feel like your linear algebra is not 100%, please consider going to review those. This class is also going to use a lot of probability. You really need to understand what a probability distribution is and what it means. And typical courses that might prepare you for that are any one of CS70, EECS 126, or STAT 134. Now, again, you don't need to have taken one of these classes if you've gotten this material somewhere else or at another university. But we're going to use a lot of probability heavily, and knowing the basics is absolutely essential if you're going to understand what we're talking about this semester. And the last thing I want to warn you about is that you really need to know how to program. And at the very least, how to debug your own code. Let me be clear that this is not a programming class. The teaching assistants are not under any obligation to look at your code. If you're having a problem with your code, maybe some of your TAs are nice enough to do it anyway, but they're going to be informed that they can quit anytime they want looking at your code. Oh, One thing that's not a prerequisite is CS 188. So again, these prerequisites, there's many different ways you could have achieved mastery of these subjects, but it's important to have mastery some way. If you're weak on one of these, please try to brush up for the next week or 3. And homework 2 will be designed to help you with that process. So let me talk about the breakdown of scores for the grades. If you are an undergrad taking CS 189, then 40% of your grade will be based on the 7 homeworks that we do this semester. Now, our late policy on homeworks is that you are given 5 slip days total for the whole semester. So if you're a day late submitting one homework, or even if you're an hour late, you've used up 1 slip day. Slip days are discrete. We count days, not hours. So if you're a little bit late, you're a day late. You can delay up to 5 days total over all 7 homeworks, and there's no penalty. If you go over your slip days, we just won't grade. Well, we will grade, but we won't count some late homework. I think the TAs will run a script that tries to choose the best homeworks to drop, but please try not to use more than 5 days of lateness this semester. And 20% of your grade will be based on the midterm, and we already have a room scheduled for the midterm. It will take place on Monday, March 20th, from 7 o'clock to 8:30 p.m. So that's kind of during class time, but the registrar is very weird about assigning rooms, and so it's half an hour later than the usual lecture time. And it'll replace the lecture that day. And that'll be in Wheeler Hall Auditorium, also known as 150 Wheeler. And 40% of your grade will be based on the final exam. And we know the time and date, but not yet the place of that exam. It'll be Friday, May 12th, from 3 to 6 p.m. So please reserve those times. It is not yet clear whether we'll be able to offer alternate times, but if we do, it'll be immediately after everybody else takes the exam. It definitely won't be on a different day. If you're a graduate student and you're taking 289A, then the breakdown is similar with one important change. Homework will still be 40%, the midterm will still be 20%, but the final exam will only be 20% of your final grade. The other 20%, you will be asked to do a group project, typically 3 to 4 of you to get working together on a common project, which you'll propose sometime around spring break and turn in at the end of the semester. And with this project, the idea is that we want it to be something that also benefits your research. So if you have some research plan that requires some machine learning, and you can figure out how to put them together and create a project that way, then that's great. We're very happy if you can make progress on your dissertation even as you're making progress on this project. So of course I have to say something about cheating. It's not allowed. But to sort of trace the boundaries, so first of all, discussion of the homework problems with your classmates is totally fine and encouraged even. With regard to code, showing other students small amounts of code, like say a 5-line snippet, is okay. But not large chunks of code. You should not be sharing large chunks of code that you've written with your classmates. Now, all of your homeworks have to ultimately be written individually. And of course, that means your programming, your computer programs, have to be programmed individually. And of course, the way that we police that is that we have computer programs that can go through millions of lines of code and check for matches, check for plagiarism, check for similarity with previous semesters, etc. And if you're caught cheating, then the typical penalty is a large negative score for the assignment on which you cheated. But that's not a promise. I reserve the right to give you an F in the course. If I feel that the violation is egregious enough, and if there's 2 violations, I'm definitely giving you an F. It's been a while since I taught CS61B, but the last time I taught it, we had to punish about 100 students in the class that our software caught cheating. It was a very painful experience, and so please don't put me through that again. It's probably why I don't teach 61B anymore. All right, that's the end of the logistics organization part of the lecture. Any questions? Mm-hmm. Oh, DSP is complicated, and we're not really sure what we're doing yet. That's always kind of arranged late. Very typically, DSP students have extra time, so sometimes we start them early, sometimes we start them late. I believe that we will not be able to use the campus proctoring service for the midterm because they won't do it after 5 p.m., and we want everyone to take the exam in the evening. For the final exam, apparently they're willing to go later. So we may have the DSP proctoring office giving final exams from 1:30 p.m. to 6 p.m., which is as late as they were willing to go on the day of the final exam. Other students who need to stay later, they'll be proctored by teaching assistants. You're welcome. Other questions? I see a hand way in the back of the corner there. Ed discussion? Yeah, it's already linked from the class webpage. I believe it's possible to add yourself. Just follow the invitation link that's on the class webpage. So yeah, you can all get on a discussion now. There are already questions and answers there. Grade scope, we'll probably get that done in the next 24 hours, but that's not done yet. Okay. Yes. The homework will all be graded by readers who are paid to read your homework. There's no self-grading, no, or no peer grading either. Mm-hmm. Oh, you do not need to request slip days. Yes, they apply automatically. We just keep track of when you submitted things and have a script that figures out your slip days. But I do want to say, though, sometimes, so about extensions, if you're not a DSP student, we're kind of reluctant to give additional extensions. I'll say more about this later in the semester, but slip days should be the whole cushion you need for most of the things that can go wrong in life, including maybe a very short illness. So if you're going to ask for an extension, you should either have a really severe situation, long-lasting illness, or be a DSP student. Having said that, we do occasionally give extensions on top of slip days, but you should always submit your homework by 5 days after the official deadline, no matter what, because the readers have to grade the homework sometime. We can only delay that so long. So thank you for that. Other questions? Way in the back there? The class is binned. I have never had to curve this class. I've used the same bins every time I taught it. Mm-hmm. Yes, the solution for the midterm will be made available publicly on the class webpage, probably within 24 hours after the midterm. The solutions to the homework, we reserve those for students who are officially enrolled in the class, but those will be available through B courses. If you're not enrolled, please don't ask. Yeah. There's no homework drops, no clobbers, nothing like that, sorry. You should do every homework, especially homework 6, the neural network homework, because if you haven't learned neural networks and programmed them, you're not a real machine learning person. Other questions? Are there going to be curved? No, nothing is curved in this class. No. I don't like curving. I do not. And I'll avoid it at all costs. Only if there's a really extreme upset in the scores would I curve. Yeah. My lecture notes that I'll be providing for this class are very concise. In a sense, they're complete, but there's kind of a lot of stuff you have to fill in. And you know, if you have a 150 IQ, you'll be able to read just the lecture notes and fill in everything that's missing. But if you have a 130 IQ, maybe you should read the class readings as well, because they'll bring up details and additional considerations that you hadn't thought of from the lectures. Yeah. I'm not planning to use Zoom for lectures this semester unless something goes terribly wrong. No, it'll be live lectures and then they're just recorded. Yeah. No, the grading bins are a secret, sorry. Making grading bins public creates endless additional work for us. We're just not willing to do that, sorry. Yeah, absolutely. Okay, I should definitely make this clear. If you are trying to get into this class, you can and should submit homeworks on time, even before you're enrolled. We will absolutely make that possible. We will give you all, probably on a discussion, the entry code for Gradescope, so you can register with Gradescope without being enrolled. You can already enroll in Ed Discussion without being enrolled. Just follow the invitation link from the class webpage. Absolutely, we not only allow, but we insist anyone who aspires to get into this class this semester to submit homeworks on time, please. Yeah. No, I'm not making lecture notes available before lecture. Sorry, I usually change them too much afterwards. Yeah. No, we have no idea what the office hours will be, nor who will be teaching which discussion. That's something we have to figure out between now and Tuesday. So let me move on now to the material of this class. So in a sense, the philosophy of machine learning, or at least as presented in this class, can be boiled down to 3 points. Given data, we are trying to find patterns in that data. And then, once we believe we've understood those patterns, we're trying to use those patterns to make predictions. So that's what machine learning tries to accomplish. How? Well, first of all, we have models of how we think the data might work, and we use statistics to flesh out those models. And so our models and our statistics help us to understand those patterns. And finally, we use optimization algorithms to learn those patterns. The optimization algorithms depend very heavily on what our models are. In this breakdown of what is machine learning, the most important part is the data. Data drives everything else. You cannot learn much if you don't have enough data. You cannot learn much if you have bad data. But it's amazing what you can do if you have lots of good data. Machine learning has changed a lot in the last couple of decades, partly because the internet has made vast quantities of data available for all kinds of learning problems. For instance, you can download tens of millions of photographs that tourists have taken on the web and use them to build a 3D model of Paris. There are people who do that. One of the interesting changes over the last decade or two is that certain techniques that had fallen out of favor, like neural networks, have come back big in recent years because researchers found that they work a whole lot better when you have massive quantities of data to throw at them. So neural networks were kind of hot in the 80s, and then they kind of died for a while, replaced by support vector machines and other models. But they made a big comeback about 10 years ago, you could say, roughly, largely because once you have enough data, they start outperforming their competitors. They only seemed weak before because we didn't have enough data to train them on and big enough computers to train them with. Now, there are several different sort of groupings or genres of learning algorithms, and the most important one is classification, though it's not the only one. But we'll spend more than half this semester on classification. And so what is classification? All right, so take a look at this scatter plot on the upper left here. This is taken from one of your textbooks, by the way. It's from Introduction to Statistical Learning. And what we're given here is a bunch of credit card data. So all these points, each one corresponds to a single borrower, or that is a single credit card holder. And for each person, we have two quantities that we know. We know the balance the average balance in their account each month, and we know their income. So there is a blue dot here that corresponds to $500 balance and $40,000 annual income. And so the blue dots are people who kept paying their credit card bills on time, and the brown dots are people who defaulted. So what we want to do is we want to take in this data, and then we want to find some way to predict some new point. Like, let's say I have a point here. There's a new borrower. I want to predict whether that borrower will default or not. How do I do that? You can look at what other points are similar to that point, close to that point. And you can also do this one component at a time. So remember, the x-axis is the balance, the average monthly balance on the account. What if you just look at the balance? Well, if you just look at the balance, you can see that there's a pretty big average difference between people who don't default and people who do default. All right, so just from balance alone, we can make pretty good predictions, but not perfect. If you look at income, well, income by itself isn't very useful for making good predictions, but it's a little bit predictive. You can see that there is a difference between the mean scores of defaulters and non-defaulters. If you look at both balance and income together, though, you can do something slightly better than just looking at the balance alone. You can find a decision boundary that cuts through the data in such a way that if you use that decision boundary to make your predictions, like you predict everyone on the right, every new borrower on the right of that line is going to default, and every new borrower on the left of the line is not going to default, this will give you a slightly more accurate prediction than if you just look at the balance, because it's a tilted line. So what we're doing is essentially there's two steps. The first is we need data, and collecting training data is not always easy, but it's not the subject of this course. So we'll assume somebody gives us the data, and the data is a set of reliable debtors and a set of defaulted debtors. And various attributes of each of those people, like their average monthly balance and their average annual income. And then, here's the magical part. Somehow we're going to evaluate new applicants and make predictions about whether they'll default or not. So prediction, that's the goal of machine learning quite often. So let's consider a situation where you just have a bunch of points that are said to be in one class, like people who don't default on their debts, and a second set of points from people who are in a different class, like people who do default on their debts. And you want to take a third point, let's say here, and so we're asking, do I think that person's going to default or not? Well, one possibility is let's look at the nearest neighbor. So in this example, the nearest training point to this new applicant is colored red, a defaulter. So we're going to predict that that new applicant is also going to default. But that's not the only way to do it. There are many, many ways to make these predictions, and some work better in different circumstances. So another thing that we will often do is we will draw a decision boundary. And sometimes it's nice to just use linear decision boundaries. So I'm just going to hypothesize that given a new borrower, if they're on the right-hand side of that line, they're probably going to default. And if they're on the left-hand side, they're probably not. Over the next few lectures, we're going to learn a lot of different ways to draw these decision boundaries. But for now, I just want to compare two methods. So essentially, these are the methods I just told you about. On the left is what's called a nearest neighbor classifier. And on the right is what's called a linear classifier. And I should say there are many different linear classifiers in the sense that there's many different ways to pick that line. We won't worry yet about what that method is. But we can see with the nearest neighbor classifier, I've drawn a decision boundary, which is this black jaggy curve here. And the fact that it is so jagged and not very straight is a natural outcome of the fact that we're just looking at the nearest neighbor to any point from the training set to try to classify any other point that's not in the training set. And actually also to classify points in the training set as well. You get a very jagged boundary on the left. You get a very straight boundary on the right. One thing, though, that this is the wrong picture. Sorry. I just realized that somehow these got swapped. Let me give you the correct figure now. All right. Pardon me? Yeah. How many of you caught it? All right. So now that I have the correct figure, you'll notice it's even more jaggy now. So the nearest neighbor classifier gives you a very jagged decision boundary. It looks a little bit crazy, and you have to ask when you look at that, do I really think that that's the right way to predict how all future borrowers will behave? Is it really that crazy? I don't know. But there is one very nice thing about the nearest neighbor classifier, which is that at least it classifies all of the training points correctly. So if a training point was a defaulter, the nearest neighbor classifier, if you hand it that same point, will say, that's a defaulter. Whereas the linear classifier doesn't necessarily do that. You could give the linear classifier one of the training points, say this non-defaulter here, and you'll notice that this blue point is on the brown side of the decision boundary. So if you ask our linear classifier, what is the correct classification for this training point, it will give you the opposite answer of the one you already told it. You know, I told you that point was blue, but you think it's brown. What the heck? Well, that makes it seem that the nearest neighbor classifier is superior to the linear classifier. The nearest neighbor classifier has a 100% accuracy rate on the training data. But that's not necessarily going to be true for predictions on new borrowers. In fact, there's a pretty good chance the linear classifier will do a better job of predicting new borrowers. Because all that jagginess on the left, that actually indicates that you've got a lot of data points that are just unusual, that don't really follow the standard pattern, and that aren't necessarily going to correctly predict how most borrowers will behave who have the same income and the same monthly balance. All right, let me show you another pair of classifiers. Here's the figure I had before. We will, all right. So I was supposed to have 2 copies of this drawing, but since I only have one, I'm moving it down. And so what we're comparing now is, again, the nearest neighbor classifier. Where you just look at the nearest neighbor among the training points to make a prediction, and what's called the 15 nearest neighbor classifier. So the idea of the 15 nearest neighbor classifier is that we're not going to look at just one nearest point. I'm going to, given a new borrower I want to make a prediction about, I'm going to find the 15 training points that are closest to that new borrower, and they're going to vote. So some of them vote default, some of them vote not default. Majority takes it. And you'll notice that although the 15 nearest neighbor classifier has a jagged boundary, it is less jagged than the 1 nearest neighbor classifier. It is more likely to reflect, probably, the reality of the situation here. And so, in most cases, the left figure is an example of what's called overfitting, where we try a little bit too hard to fit our decision boundary to the data and wind up getting something that isn't necessarily going to predict future data very well. The decision boundary is just too intricate to be believable. In the right figure, the decision boundary is smoother. It's not perfectly smooth, but it's a lot more plausible as an actual statistical model of how reality works. So, any questions about this? Mm-hmm. 1. Yeah, the left is 1 nearest neighbor. You could call it the nearest neighbor classifier, or you could call it the, hey, don't do that. You could call it the 1 nearest neighbor classifier. Yeah. The question is, do I give different neighbors different weights according to their distance from the new point? You can do that. Some people do that. It's not the standard technique. If I tell you 15 nearest neighbors, you should assume that they all have the same weight. But yeah, you might get better answers by weighting the points according to their distance from the query point. Yeah? The question is, how smooth could we get a k-nearest neighbor classifier? And, well, even in theory, for any large amount of data, it is going to be pretty jagged unless you arrange the data just in some way that would never really happen in reality. But, I mean, you can always make an artificial data set like this where you perfectly space the points in such a way that the nearest neighbor classifier will actually be a linear classifier. You can do that, but that's not what real data sets ever look like. So in theory, perfectly straight. In practice, that never happens. There's 2 questions in the back. Let me start with the black shirt. Is there a k where it becomes unnecessary to increase k? I'm going to give you a sophisticated answer to that question soon. The answer is maybe not, but validation will tell us what the right k is. So wait for that a few minutes. The other question? Yeah. For a neural network, you can draw a decision boundary just like this. And quite often it will look a lot like one of these decision boundaries. It's straightforward to draw the decision boundary for a neural network, except for the fact that usually your data is in a pretty high-dimensional space. So it's hard to visualize it, but in principle, it's easy to figure out what the decision boundary of a neural network is. And that decision boundary is generally very sinuous. The precise shape will depend on what types of unit nonlinearities you're using. If you're using ReLUs, it'll be jaggy and straight like this. If you're using sigmoids, it'll be nice curves. Anyway, this is all getting ahead of us because most people don't know what we're talking about, but I hope that answers your question. Yeah. I would say that nearest neighbors, the further away you are from the nearest neighbor, the less likely the prediction is to be accurate, as a rule of thumb. Having said that, virtually all classification methods are bad at extrapolation. So if you're trying to predict a point that's well outside the range of the rest of the data, almost no classifier works very well. But oddly, nearest neighbor classifiers are one of the very best in that circumstance, because that's the best you can do is find the nearest neighbor. Yeah? Can you have an even number of neighbors? If you set k to be even, you have the question of what do you do when there's a tie? So that's why k is almost always chosen to be odd. But if you have a multi-class problem with more than 2 classes, then that problem comes up anyway, and you just have to make an arbitrary decision about what to do when there's a tie. Mm-hmm. Well, how do we do optimization? Nearest neighbors is unusual in it that it's essentially a method that requires no optimization at all. It's the only machine learning algorithm where the pre-processing time is essentially 0. But you pay for that with the cost later on. When you do a query, you have to look at every point in the training set. That's expensive. I just want to very briefly tell you what you're going to be doing on homework 1. You'll be classifying digits as well as spam and several other things. But just to think about what it means to classify digits, we're going to give you these little bitmaps where, well, they're not just bits because there are intensities. But here, the top row is a bunch of handwritten 7s written by many different people. The bottom row is a bunch of handwritten 1s written by many different people. We are going to give you, with homework 1, examples of all 10 digits, and then ask you to create a classifier that can, say, distinguish 2 digits or distinguish them all. Now, before you can classify these, you have to somehow encode them. So you have to express those as some number that you can put into your classifier. And the way that we're going to do that most commonly is the simplest thing you could possibly think of, which is you just turn the bitmap into a vector of values. So, if you had, just to give a smaller example, a 4x4 bitmap with these intensity values in it, then the simplest way, but not necessarily the best way, to turn that into data to input into your classification algorithm is just to write it out as a vector, where you copy all the values from the bitmap into one long chain. Now, in lecture 4, I will give you an alternative way to do it, that it involves using an edge detection algorithm. But for homework 1, this will suffice. You'll be able to do homework 1 just by using that as your input and training a linear classifier to try to separate in this high-dimensional space. Like, for instance, in this example, this is a point in a 16-dimensional space. And so you need to get used to thinking of your data as points in some high-dimensional space, which is a little hard to grasp, but your intuition for 2D and 3D geometry will help a lot with 16-dimensional geometry as well. When we have a linear decision boundary, because we're using a linear classifier in some high-dimensional space, that's called a hyperplane. So, in this example, we just used a line to separate the data. But that's because this is a two-dimensional space where the dimensions are income and bank balance, or credit card balance. Often you'll have more than 2 pieces of data about each person you want to analyze, and so maybe you're working in a 100-dimensional space and not a 2-dimensional space. Well, we still have linear decision boundaries, but now they are the 100-dimensional analog of a line. So the hyperplane will be a 99-dimensional surface that cuts your 100-dimensional space into 2 pieces. We'll have more time to develop intuition for that throughout this semester. Now, the last big topic I want to hit today is really very important and crucial. Testing and validation. This is stuff at the very heart of what machine learning people do. And so there are 2 steps here. You train a classifier. So when you do that, the classifier learns to distinguish 7 from not 7, let's say. And maybe a different classifier learns to distinguish 1 from not 1, and so on for each digit. Once you've trained it, we want to test the classifier on new images. Because that's what allows us to figure out whether you've done a good job, whether you trained your classifier smartly or dumbly, whether your model was an effective model or the wrong model for how these digits are spread out in space, in 16-dimensional space. And between training and testing, we have 2 different kinds of error called training error and testing error. So the training set error, or just training error for short, is the fraction of training images that are not classified correctly by the classifier that you've just trained. Whereas the test set error, well, we assume that now you're getting a bunch of new people to draw 7s or 1s or other digits on paper, and now you're using those to test whether your classifier can correctly read the digit. So now that's going to be the fraction of misclassified new images. And what I mean by new is that they're not ones you used for training. By the way, when I underline words, I'm giving you a definition. So always look at the underlined stuff and try to memorize that term so that you'll have the definition memorized. So now we can talk about some of the strange things that happen in machine learning, like outliers. When I talk about an outlier, I'm talking about a training point, or maybe a test point, whose labels are atypical. So a simple example of that would be a solvent borrower, someone who could have easily paid the bills, but defaulted anyway. And for that matter, an outlier could also be a solvent borrower who didn't default, but your data entry clerk put the wrong label in and said that they did default. So when we go back, say, to our nearest neighbor classifier, well, there's a strong case to be made that maybe this point is an outlier. Maybe it's not the case that most borrowers at that in that location are going to fail not to default. Maybe this is just an unusual person. And that's part of why we get these jaggies, is because some people are just outliers who don't go with the other people who are like them. And again, I mentioned overfitting, and I want to mention it again. Overfitting is essentially what happens when the test error deteriorates because the classifier just becomes too sensitive to outliers or other spurious patterns. So when you have a lot of outliers, that's a situation where a linear classifier might work better than a nearest neighbor classifier, because the linear classifier isn't fooled by a few outliers. It sees through them and adapts itself to the majority of votes and ignores the few crazies who don't do things the way they're supposed to. On the other hand, if there aren't a lot of outliers, if your training data really is an accurate characterization of the space, then maybe the nearest neighbor classifier will work better. Now, in machine learning, the goal is to create a classifier that generalizes to new examples we haven't seen yet. And overfitting is counterproductive to that goal, so we're always seeking a compromise. We want decision boundaries that make fine distinctions but aren't outright superstitious. I will demonstrate that by talking about the k in k nearest neighbors and how we choose that. So when we're deciding how many nearest neighbors we should look at to vote, that's an example of something called a hyperparameter. The k in k nearest neighbors is a hyperparameter that governs how the algorithm behaves. And in most machine learning algorithms, the important hyperparameters essentially give you a dial that you can use to move between overfitting and underfitting. And the textbook has a very nice image to illustrate that, but I've added some things that weren't in the original textbook image. So this is a graph showing the k-nearest neighbor algorithm's performance on a wide variety of different k's. Now, the graph is a little bit confusing because the horizontal axis here is k, but you'll notice that the smallest number is on the right. So points on the far right of the graph are the one nearest neighbor algorithm. At the other extreme, we've got 151 nearest neighbors, and I think there are only 151 points in this problem, so that's kind of a stupid algorithm too. But in the middle, you have 5 nearest neighbors, 21 nearest neighbors, 69 nearest neighbors, all ones that might plausibly be good. But which one's the best? Well, one thing you'll notice about k nearest neighbors is that if you only look at the training error, it seems like you should make k as small as possible. You'll notice that in this graph of training error versus k, high values of k give you a huge training error, whereas as k gets smaller and smaller, the training error tends to drop. Not monotonically, but close enough. So one nearest neighbor seems like the ideal algorithm when you look at training error. But when you look at test error, wait, it's not like training error. It's very different. It's a smile. Our graph is a smile. What does that mean? Well, basically what it means is that if you make k too small, you tend to overfit. You have all these jagged boundaries that don't reflect reality. But if you make k too large, you tend to underfit, meaning you're looking at too many neighbors, and so you just lose accuracy. You're not making good predictions anymore. And typically what we find is that the ideal classifier is somewhere in the middle. We're navigating this trade-off between underfitting and overfitting. And in this particular example, 7 nearest neighbors is what works best with this particular test set of points. And so what we want to do when we train a machine learning algorithm like k nearest neighbors is not only to train it, but to train it multiple times with different values of k, or some other hyperparameter that navigates between underfitting and overfitting, and look for the optimal point. And to look for the optimal point, we need test data for which we know the labels so that we can actually draw that test error graph. And so doing that is that the process of finding the optimal k is called validation. Validation is how we're going to select our hyperparameters. And so the idea of validation is that you need test data for which you know the labels. Well, typically what happens is somebody just gives you a big batch of training data with labels, and you hold back a subset of the labeled data, and you don't use it for training. So the subset of labeled data that you randomly select from the data you're given, that is called the validation set. And once you have selected your validation set, you don't use it to train your classifier. But what you do is you train your classifier multiple times with the data that's left over, not in the validation set. And you do it with multiple times with different hyperparameter settings. Then what you do is you take that series of classifiers that you've trained, each with a different k value, and you run the test data through all of them, and you see who scores the best on the test data, or sorry, the validation set, pardon me. So choose the hyperparameters that work best on the validation set, and that's your classifier. All right, so if you understand how this is supposed to work and why, then it's important to realize that we now have 3 different sets, potentially, of data. You've got the training set, which is the points you actually use to train. So those are used to learn the model weights through some optimization algorithm. Then you've got the validation set, which is used to tune the hyperparameters to figure out which value of k is most likely to be the right one for your particular data. And the validation set allows you to choose between different models. Each value of k that we tried gives us a different model, a different classifier. And we want to choose the best model among those models. The validation set tells us how to do that. And then thirdly, sometimes optionally, there's something called a test set. And the test set is meant to be used as a final evaluation of the model. And kind of what characterizes the test set is we don't give you the labels for the test set. The test set, essentially, you can think of it as being stored in a vault where you can't touch it while you're training your classifier. You can't even touch it while you're choosing your hyperparameters. It's kept with the intention that you will run the test set once at the very end. And in fact, it might not be you who runs the test set. It might be someone else who takes your model, applies it to the data. This other person knows the correct labels, but you don't. And so this other person tells you, oh, you scored 56% on the test set. Now, it's considered very bad form to look at the test set more than once at the end. Yeah, if researchers in medicine or pharmaceuticals peek into the test set prematurely, they could wind up with a classifier that's just wrong and endangers lives. So the way that we're going to accustom you to this concept in this class is through a website called Kaggle.com, which runs machine learning competitions. Including most of our homeworks will have some Kaggle portion. And we use 2 data sets. We give you a bunch of data that is labeled. And so you can use those to train, and you can also use them to validate. And then there is another set called the test set, where we're not going to give you the labels, but Kaggle.com will know the labels. And you're going to submit your predictions to Kaggle.com, and Kaggle.com is going to tell you your score, your accuracy rate. And so if your public results are a lot better than your private results, we will know that your model overfits the data. One last point I want to make about these 3 sets is, in one sense, the validation set is like the training set. What they have in common is that you have labels for both the training set and the validation set, whereas for the test set, you do not. But on the other hand, there's also a sense in which the validation set is like the test set, because essentially they're both used for testing your classifiers. So the validation set sort of in the middle between the training data and the test data, in a sense. Any questions about any of this? what does hyperparameter mean? Or oh, the purple line. Well, I was hoping nobody would ask, but the purple line is what's called it is the test error on what is called the Bayes optimal classifier. The Bayes optimal classifier is essentially the best classifier you could get if you knew the underlying probability distributions that were used to create this data in the first place. And so in lectures 6 and 7 or so, we'll learn about Bayes optimal decision boundaries and what that means. But the main point is that you cannot expect the test error to go below the purple line, regardless of what k you choose. Unfortunately, you can never know where that purple line is unless you generated the data from some artificial process. Question here.
So going back to the decision boundary graphs,
Mm-hmm.
how would we know potentially we would benefit from an extra dimension to our data? So like the
Well,
proxies we use.
yeah. How would you know if you could benefit from an extra dimension to your data? The answer is add that extra dimension, run that model again with validation. Validation will tell you whether adding that new feature improved your predictions or not. Sometimes it makes the predictions worse, so it could go both ways. But validation is kind of the answer to everything. Mm-hmm.
I have a question on this validation process. Once we have sort of identified the hyperparameters that we want to use, would we want to redo that validation set in our training data and run the model again, or would we want to just use the model that we ran after training?
Would you want to, so the question is, would you want to include the validation data in the, I assume you mean, now that we've figured out what the optimal value of k, let's include the validation data in the training set and retrain the classifier on all the data, both our original training data and our validation data, and that gives us the final classifier. And the answer is that is in fact done very often. Not always, but it is very often done, yes. Because you might get a slightly better classifier. Once you know the right hyperparameters, you might get a slightly better classifier by using all the training data to train, or all the labeled data to train, to be precise. Yeah, so good question. You, sir, in the brown coat. Is there an optimal ratio between the test error and the training error? Sorry, not optimal. Is there a commonly found ratio between the training error and the test error is the question. And, well, I will say that it's extremely rare for the test error to be lower than the training error. That would be weird. But other than that, almost any ratio is possible if your training and test errors, if the ratio is close to 1, that means that you're not overfitting too badly. If the ratio is very far from 1, you're probably overfitting badly. Anything is possible depending on how your hyperparameters are chosen and whether or not the model itself is a good model. It may be that linear classifiers are a terrible model for your data. It may be that they're a great model, and that's going to affect the ratio that you get between training error and test error very much. No, I don't think there is a typical number. Like he's saying the ratio between these 2 points at the best value of k, the ratio here, maybe it's 1.5 or 2 or something. Nah, it's not that predictable. It could be anything. Green shirt. Is this best k value also true in the overparameterized regime? Well, By over-parameterized, do you mean you have a lot of spurious features, a lot of spurious dimensions? Oh. Oh, in your model. Oh, that can be a very complicated subject, yeah. But, sorry, can you ask the original question one more time? Okay, so almost certainly you're talking about neural networks, I would think, because this bizarre behavior of when you really over-parameterize, you have what sort of a double U-shaped curve. It's called, I forget what it's called, double something. That is a more complicated subject that is not exhibited by all learning algorithms, but neural networks seem to be particularly odd in that respect. It's kind of an advanced topic, and I think that researchers are still trying to understand it. Sorry, it only applies to, well, it's not going to apply to your nearest neighbors. It'll apply to neural nets. There are probably other learning algorithms it applies to, but I don't know what. So let me check the time. One more minute. Question in the back, black shirt or black? Okay. I'm sorry, can you stand up and talk louder? I'm having a hard time hearing you. Oh, is dimensionality a parameter? Not exactly, but we will nevertheless discover later in the semester that sometimes you get better models by removing some of the parameters. And we will still use validation to decide which parameters we should remove. All right, so it's time, and thank you very much for your time and attention. See you next Monday. And if you have further questions, feel free to come chat with me.